Welcome back to eCoreAcademy, everyone. My name is Anita Raj, and I'm one of the co-founders here, along with my younger brother, AJ Raj. As you can see, we have a new Algebra 2 lesson today, and we're going to be continuing with our lessons on logarithmic functions, which are the inverses of exponential functions. Again, this lesson was specifically requested by some students here in India who are preparing for some exams. So once again, if you have any requests for lessons, please feel free to reach out to us and let us know so that we can prioritize what you need. In this lesson, this is going to be lesson 2, by the way, we're going to be evaluating and using a log scale. So we're going to have our first problem going to be on evaluating logs, and then the second problem is actually going to be a word problem where we're going to be using a log scale before that we'll learn exactly what a log scale is. So in this lesson specifically, we're going to learn how to find the values of logs. That's what evaluating means. Evaluating means finding the value of, or the numerical mathematical equivalent of. Then we're going to understand what common logs are. These are the logs you'll see that have a base 10. We're going to then use a log scale, and we're going to understand what a log scale is, and then realistic applications for that. And then we're going to end this video doing a word problem using the Richter scale, which is a measurement of earthquake magnitude. Before I get into the video, there are 2 things I want to do. First, I want to show you the shirt I have on. It's actually an eCoreAcademy merch t-shirt that we use for our hospital medical supplies drive. You can check that out in a previous video. This is the shirt that we use, and we want to see if maybe you or students are interested in getting these shirts for yourselves. They're really nice quality, so if you're interested, please let us know so that maybe we can think about opening some sort of merch store where you can get our merch and you can wear it. And then secondly, before I even get into the lesson, I'd really appreciate it if you could like, subscribe, hit the post notification bell, drop a comment down below, and share using our socials. So let's get right into this video. We did problem number 1 in the last video, introduction, so I highly suggest you go check that out. Now we're going to do problem 2, and that's going to be evaluating the logarithm. So we're finding the mathematical equivalent. So we're pretty much, what's going to happen is on assessment, you'll be given a question like the one you see up here. So what is the value of log base 8 of 32? Okay, we are pretty familiar with how logs look right now. However, in this log, we're missing the equal sign. In order to be an equation, which this is, it's the equation of a function, a log function, you need an equal sign. In this case, we don't have an equal sign, so we're trying to find the value of the log, so we're actually trying to solve this log or evaluate it. In order to do that, there are 6 steps you're going to have to follow that are broken down in this slide, but then as you see on the next slide and as we go on, those steps become automatic, some even combined together in the workouts that I show you to solve the problems. But these are the 6 steps that you can maybe jot down in a notebook or wherever you're taking notes that you can mentally go through every time you're solving a log, and these are guaranteed to get you the right answer. And then the last step I'll show you, it's optional, but it's definitely something you can use in order to check to make sure you got the right answer. And remember, in math, we love the problems where we get an answer to our problem, but then we can plug it back into the original problem and make sure that our answer is correct. The first step is to write a logarithmic equation. So an equation has an equal sign. An expression, which is pretty much what we have in the problem given log base 8 of 32 without the equal sign, well, an expression is just that, it's a mathematical series that does not have an equal sign. So we need to first write a log equation. In order to do that, all we're going to do is write an equal sign, and then we're going to put an x. So where the x right now is, an x is a variable or placeholder. This x is going to be the exponent that we're solving for, because remember, what we're solving for, the value of this log, when we solve for it, we're actually finding x, which is the exponent. So if we write this in exponential form, we're solving for the exponent given the base and the answer. So whatever the base is raised to, that's 32. So the base in this case is 8, the answer is 32. We're trying to find x, which is the exponent. So we're going to write equals x. Our second step is we're going to use the definition of a log to write exponential to write an exponential equation. So if you remember from the last video, we were talking about converting between logarithmic form and then exponential form. In order to convert from logarithmic form to exponential form, you can draw that e. So when you draw that e, you can pretty much figure out what order the three numbers have to go in. In this case, our three numbers in log form are 8x and 32. If we draw that e, we see that 8 comes first, so it's the base. X comes next, so it's the exponent, then we're going to write our equal sign, and then 32 comes last. So in this case, if we're writing this log in x as an exponential equation, it's 8x, 8 to the power of x equals 32. We're trying to find out what power we're raising 8 to, so that's x, that's an unknown power, to get 32. The next step is to write each side using base 2. So what does this mean? So right now our base is 8 on the left side, and on the right side we just have 32. We would want to rewrite these two so they have a common base, so a common number that is being raised to an exponent. If you look at 8 and 32, they're both powers of 2. So if we raise 2 to the third power, 2 cubed, we get 8. So 8 is a perfect cube. If we raise 2 to the fifth power, we get 32. Because what happens is 2 cubed is 8. If we raise 2 to the fourth power, we're multiplying 8 times 2 to get 16. And if we're raising 2 to the fifth power, we're multiplying 16 times 2 and we get 32. So 8 is equal to 2 cubed and 32 is equal to 2 to the fifth. Now you can see that 2 and 2 are on both sides of the equation. We have the same base and it's 2. As you can see as well, we put a set of parentheses around the 2 cubed because we're raising 2 to the third power first, which is 8, and then we're raising that 8 to the x. So you have to include those parentheses. And on the right side, we just write 2 to the fifth. Next, we know the power property of exponents. So what is the power property of exponents? Hopefully you've covered more about these properties of exponents in Algebra 1, but the power property we're going to use here is when you see those parentheses, you're pretty much raising the whole quantity 2 cubed, which is equal to 8, but you're raising that whole quantity 2 cubed to the power of x. When you do that, what's happening is you are multiplying the two exponents. So when you raise a power to a power, you multiply the two powers together. In this case, we're raising 3 to the power of x. So you're multiplying 3 and x, and you're going to get 3x. That's how we get 2 to the power of 3x now, because we multiply the 3 and x, and that's going to be equal to 2 to the power of 2 to the fifth power. Since both of the bases are equal to each other, another property you can use is when the bases are equal to each other, the exponents are also equal. So for example, if we have something like 1 to the fifth power equals, it's set in such a way that if you have the same bases equal to each other, if you have the same base and the exponents are equal to each other, that means that both sides of the equation are equal. So whatever I get on the left side, even after I raise the number to whatever power and get that final answer, it's going to be equal to whatever is on the right side after I raise that number to whatever power because they have the same base. So in this case, you can pretty much remove the bases out, and so you can set just the exponents equal to each other so we can actually solve. So we're going to remove the 2's and we're just going to set the exponent 3x equal to the exponent 5. And our last step, we're doing simple algebra and solving for x. To get x by itself, we're going to divide both sides by 3, so x is going to be equal to 5/3. And that is how you evaluate a log. In order to check, what you can do is you can actually take the original log base 8 of 32, set that equal to 5/3, because remember we were setting it equal to x, and we found x is equal to 5/3. Logs are equal to the exponent, so we're setting it equal to 5/3. Now we're going to rewrite this in exponential form. We're going to just do 8 to the power of 5/3, and we're going to solve that. And if we get 32 as our final answer, that means that we solved for x correctly. So if we raise 8 to the power of 5/3, well, that's a bit difficult. We're going to have to implement indexes and radicals. That's a bit complicated. So what we can do is we can take 8, which is the base, and we can rewrite it as 2 cubed, and I'll show you exactly why we're doing that. We already found 2 cubed. We know that 2 cubed is equal to 8. What we can do is we can put a set of parentheses around 2 cubed, and that 2 cubed is going to be raised to the power of 5/3 that the 8 was originally raised to. Now you can use the power property and multiply the exponent of 3 with the 2 with the 5/3. When you multiply those two together, the 3's are going to cancel out, and you're going to be left with 5. So you're pretty much raising 2 to the power of 5, and 2 to the fifth power is equal to 32. So we solved this problem correctly, and that's a way you can use to check. So just continuing along with problem number 2 on evaluating a logarithm, we're going to find what is the value of each of these logs that is shown below. So we actually have 3. So these are just problems like the last one we did, but we're going to be going through them pretty quickly just so you have more practice. So the first log we've been given is log base 5 of 125. What we're going to do is we're going to set log base 5 of 125 equal to x first because we're solving for the exponent. Then we're going to rewrite an exponential form. So we're going to raise 5 to the power of x. If we draw that e, 5 to the power of x is equal to 125. We're going to make both of these bases the same. So in this case, the base is 5. So we have 3 at 125 in terms of base 5. And luckily for us, 5 cubed is equal to 125. 5 times 5 is 25, times 5 is 125. So we have 5x is equal to 5 cubed. Now that the bases are the same, we can set the exponents equal to each other because they must be equal. Therefore, x, which is the power of the bases raised to on the left side, is equal to 3, which is the power of the bases raised to on the right side. So we get x is equal to 3. We know the final log of base 5 of 125 is equal to 3. The next problem, log base 4 of 32. So first we're going to set this equal to x because we're solving for the exponent. We're going to write this in exponential form, so if you draw that e, you'll get 4 to the power of x is equal to 32. Now we have to write both sides of the equation on the same base. However, when we look at 4 raised to any power, an integer power, does not equal 32. 4 to the first power is 4, 4 to the second power is 16, 4 to the third power is 64. So it actually skips over 32. So we need to find a similar base between 4 and 32, and that would be 2. So 2 squared is equal to 4, and then 2 to the fifth is equal to 32. So the right side we rewrite as 2 to the fifth, and if we use the power property of exponents, we're multiplying the x that was up here with the 2 that went with the 2 squared, and we're going to get 2 to the power of 2x. Because the bases are equal, we set the exponents equal to each other, so we get 2x equals 5. To get x by itself, we divide both sides by 2, and we find that log base 4 of 32 is equal to 5 over 2. And the last problem, log base 64 of 1 over 32. We haven't worked with fractions, so this is a good problem to do, especially if you're in like an algebra 2 honors class. So we're first going to set this log equal to x, and then we're going to write it in exponential form. So if you draw the imaginary e, you're going to raise this 64 at the base of the log to the power of x, and you're going to set that equal to 1 over 32. Now you need to write the 64 and the 1 over 32 in the same base. And if you look at 64 and 32, the same base would be 2, but you need to find the correct power you would raise each side to. 2 to the fifth power, as we know, is equal to 32. If we multiply that one by another 2, we get 64. So 2 to the sixth power, we're adding one more 2, is equal to 64. And if we use the power property, we're multiplying the exponent of 6 times the exponent of x, and we're going to get 2 to the power of 6x. Then if you look on the right side, you have 1 over 32. If you look at the denominator, which is 32, we know that 2 to the fifth power is 32. If you recall, when we have a negative exponent, we actually flip. So let's say if we had 2 to the fifth power, that would be equal to 32. If we had 2 to the negative fifth power, we still have that 32, but we're taking the reciprocal. So you're pushing that number into the denominator, and you're going to get 1 over 32. I'll give you another example. 2 squared is equal to 4, as we know, but if we did 2 to the power of negative 2, we get 1 over 4. So that 4, which was the square, is pushed to the denominator. So in this case, our answer would be 2 to the negative fifth, which is equal to 1 over 32. Since the bases are equal, we can set the exponents equal to each other. We'll get 6x is equal to negative 5, and to get x by itself, divide both sides by 6, and you get x equals negative 5, 6. Therefore, your log base 64 of 1 over 32 is equal to negative 5, 6. So this is pretty much how you would evaluate a log. So let's continue on, and now let's talk more about the log scale. We'll cover those common logarithms a little bit more in the next lesson because they're not exactly as relevant to this lesson, but we'll go more into depth about them. But for now, let's focus more on the log scale. We didn't go too much into depth about this when I was in class, but it's definitely something to take into consideration because you might see word problems, those tricky word problems that always trip us up on assessments or homework or anything like that. And it's important to understand what the log scale is, how it's used, and then some common realistic applications of it, like how is it actually used. So the log scale consists of many measurements of physical phenomena and have such a wide range of values. So things like earthquakes and hurricanes, those are major physical phenomena, and even things maybe in physics and science To measure these enormous physical phenomena that we just cannot measure with our regular measurement system because they have such a wide range of values that are so large, we actually write them in terms of a log scale. So these reported measurements that we find that are just way too big in order to record and track in regards to just common measurement systems, like for example the imperial system and things like that, we instead use logs, which are pretty much exponents of the values. We don't use the values themselves. For example, if we're thinking about a number that's like 1 trillion, like a trillion or even larger than that, instead of having to write out that whole number, we could just say 10 to the power of whatever it is. So we can, in that case, we're using exponents and logs. So that's where a log scale would come in handy. When you use the log of a quantity instead of the quantity itself, you're using a log scale. So instead of writing like a number that's like greater than 1 trillion, like an enormous number, when I don't write out that whole number, when I instead write 10 to some power, I'm using a log scale because I'm not writing the entire quantity. I'm simplifying it in regards to a log, which is 10 to some power. So in that case, we are using a log scale. The Richter scale isn't a log scale. So the Richter scale was developed by Charles Richter in 1935 at the California Institute of Technology, and it's pretty much a comparison that helps you determine how extreme an earthquake is. An earthquake, remember, is pretty much when tectonic plates rub against each other and cause shaking. It's pretty much recorded using a seismograph and then measuring the amplitude of the waves given off during that collision of tectonic plates. So what happens is, in order to measure earthquake magnitude across different earthquakes so that we can compare them, the Richter scale actually gives log measurement of the earthquake magnitude. These magnitudes are so enormous, and I'll actually show you the scale now, the Richter scale here. These magnitudes are so enormous that we actually have to use logs, because look how much more efficient. If you looked at the Richter scale image I have down here, we can just raise these values to a power instead of writing it all out. So if, for example, E30 to the power of 7, what would happen if we had to write out that whole number? Well, we're simplifying it by just raising each of these values to an exponent. So this is considered a log scale. So we're going to do a word problem. Problem number 3 is going to be a realistic application using the Richter scale. And I know this is wordy, but I'll help you break it down. I think this is a good example of being given a problem where you're given so much information, so much background information that you really don't need, and then pulling out the essentials to answer an actually relatively simple question at the end. So let's read the problem. In December 2004, so what's this year, 2021, that's about 17 years, 2021, so that's about 17 years ago, an earthquake with magnitude 9.3 on the Richter scale hit off of the northwest coast of Sumatra. So that is actually an island in Indonesia. I think it's near the island of Java. It's like west of Java. And then there's like another Malay island. It's somewhere in that area. So this is an island, and remember, if you like science, you probably know that islands are often stricken by volcanoes and earthquake problems and stuff like that. So Sumatra has been hit by an earthquake in December of 2004 with a magnitude of 9.3. The diagram that I'm going to show you shows the magnitude of another earthquake that also hit Sumatra, but a few months later in March of 2005. Then we're told that the formula log I subscript 1 and I2 equals M1 minus M2, and this will pretty much compare the intensity levels of earthquakes. So if we take one earthquake and we're trying to compare how intense was it compared to another one, we can use this formula. And in this formula, the variable I is the intensity level determined by a seismograph, and then M is the magnitude on the Richter scale. So M is the value in this case that we've been given, which is 9.3. So the question we're being asked essentially is, how many more times intense was the December earthquake in Sumatra, the one with magnitude 9.3, compared to the March earthquake, which we don't know yet, but I'll show you this diagram. That's the solution, but I'll show you this diagram. So here you can see where Sumatra is located. Here's the island. Here is Malaysia, Indonesia down here, and then Thailand up here in the mainland. So here we can see this is the March earthquake, and this is the epicenter. So the epicenter is a location on the surface of the earth right above where the earthquake is happening within the crust. So the magnitude of this earthquake we're being told is 8.7 compared to the magnitude of the December earthquake, which is 9.3. So we're trying to determine how intense were these two earthquakes compared to each other. So let's use the formula we've been given, which is log I1 divided by log I2 is equal to, well, we're trying to take the magnitude of the first earthquake minus the magnitude of the second earthquake. So we're taking the magnitude of 9.3, which is the December earthquake, minus the magnitude of 8.7, which was the March earthquake. We subtract those, 9.3 minus 8.7 is 0.6. So the log is equal to 0.6. With the common log, that's what we were going to cover, but we'll save it for the next video. When you don't have, you can see there's no base written here. When you don't have a base written, you can assume that the base is 10, because 10 is the common log. So in this case, the base is going to be 10. We're going to assume there's a 10 right here, and we're going to rewrite this in exponential form. So we're going to write this as 10, which is the base, because this is a common log, is raised to the power 0.6, because this is the exponent. Remember, when we set a log equal to something, the one on whatever's on the other side of the equal sign is the exponent. We write it in exponential form. So 10 to the power of 0.6 is going to determine the intensity of one of the earthquakes divided by the intensity of the other one. So if we raise 10 to the power of 0.6, if you put that in a calculator, you're going to get 4. So that is the comparison of the intensities between the December and March earthquakes in Sumatra. So that's it for the video today. I hope you enjoyed it, and if you did, please stick around for more videos like this one. There's going to be, I think, about 3 more videos coming out all about logs. Again, if you enjoyed the video, we'd really appreciate it if you could like, subscribe, hit the post notification bell, drop a comment down below, and share using our socials. Also, check out our website and Gmail. Thank you for watching. I'll see you in the next videos. Bye!